Hey everyone, how's it going? Today we're going to be going over chapter 23. So we'll be going over the Aldol condensation, some mechanisms behind it, and some practice reactions. And then we'll be looking at some interesting biochemistry applications of these reactions. So let's jump into it. What's an aldol condensation? So an aldol condensation takes place between two carbonyl groups. They can be either aldehydes or ketones. And what's going to happen is you use it in a strong acid or strong base. So here we have NaOH, that's going to be the strong base. And what it's going to do is it's going to abstract a proton from the alpha carbon of your carbonyl group. And when it does this, it forms an enolate. So now this enolate can act as a nucleophile, and it's going to attack this red acetone we have. So it's going to attack this electrophilic center, and it's going to push up this pi bond onto the oxygen. So we should get something like this. And I'm going to use purple for the bond that just formed from this arrow right here. And this was the nucleophile we used. So now we know that this negative charge can't stay there, so we're just going to replace it. It's going to grab a proton from solution. So you're going to end up with this product right here, and what it's called is it's a beta hydroxyl carbonyl. So we have a hydroxyl right over here, and we have a carbonyl group over here, and they're beta to each other because if we start from this carbon, this is the alpha carbon right next to it, and then this is the beta carbon. So this is the functional group you get from an aldol formation. But there's two types of reactions that go into this. One is the aldol formation, which we just made. Another one is the aldol condensation. Now, if you guys know what the word condensation means, it's just when water is formed, right? So you need to somehow take water out of here. Well, okay, we have an OH right here, so that's part of it. What's left, we need to take out a hydrogen. So we can take a hydrogen from the center over here. And what that will leave us with is a beta hydroxyalkene. So let's draw what that looks like over here. So what happened here was there's also a proton, and we took out this OH and we took out this hydrogen. But when that happens, we form a double bond over here in order to account for the octet rule. So that's why we get this compound over here. So this is the condensation because in this process, H2O was released. And this aldol condensation happens when you add heat to your aldol formation product. So it's a two-step reaction, sort of. The first step, you add base or acid to get your aldol formation. In your second step, you can add heat to get your aldol condensation product. So this is pretty interesting. Let's look at the mechanisms that can go into it. There's two separate types of mechanisms. The more common one is the base catalyzed, and then there's the acid catalyzed. So let's go over what happens. So in your base catalyzed, you have your aldehyde you start off with. So let's just draw it in blue so we can keep track of what we're dealing with. So this aldehyde right here in blue is deprotonated by the strong base in solution. So you're going to get an enolate over here. So this enolate came from this blue aldehyde. And this one right here is the same enolate as shown on the second step. This enolate is now going to attack the aldehyde on the left. So this is a separate aldehyde, so let's draw it in red. And what's going to happen is it's going to use this lone pairs to come in here, attack the electrophilic center, and push up. So you should get this where there's still a negative charge on the carbon. So this O- right here, it came from the red aldehyde. And the already formed aldehyde is from the blue one. This black bond in the middle is the one we just formed. And now we just need to get rid of this negative charge. So your negative charge on your oxygen just grabs a proton from water, and it gets protonated to form your beta hydroxy aldehyde in this case. So now this is your step 1 is finished. You just created your aldol formation. Now there's an optional step 2 if you add heat to get your aldol condensation, where water leaves and you form a double bond. So that's what we're going to do now. In this case, we know we have to get rid of this OH, and the normal way you would think about it, let's protonate it to form a good leaving group, oxonium cation. We can't do that in this case. The reason why is because we're working in base, and base won't allow you to protonate an OH. The pKs just don't work out. So we're going to be introduced to a new type of reaction in this two-step mechanism. The first thing that happens is your strong base is going to deprotonate this alpha carbon. So let's draw that in right here. So it's going to use its lone pairs to abstract this proton and push this bond back. So you get something like this. Now your carb anion is just going to now attack and then push up this OH. So this OH is just able to leave even with that being a good leaving group. And this is a special type of reaction called an E1CB reaction. It's similar to your E2 and E1. So let's just see what the contrasts are. For an E2 reaction, you have a strong base, and you have a good leaving group. So your base is going to attack, grab the proton, double bond is formed, and the leaving group is kicked off in a concerted mechanism. With E1, you have a good leaving group, but your base is kind of crappy. Here you have water. So what's going to happen is your water isn't strong enough to grab that proton on its own. So the first thing that's going to happen is you're going to push off this good leaving group, so you end up forming a secondary carbocation. And now taking the proton is easier because taking the proton will allow you to fill up this carbocation, which is stabilizing. So now your water is able to take off this proton and get rid of this carbocation, forming propene. So this is E2 and E1. In both steps, your leaving group leaves first. However, here, what we notice is the base attacks the proton first, and then in the second step, the leaving group leaves. So this is a sort of new spin on this reaction we've seen so much. So it's an interesting type, so pay close attention to that. Alright, so now let's go into the acid catalyzed form of aldol condensation. So we know whenever we're in acid, we have to protonate our carbonyl. The reason why is because it makes it a better electrophile. So in this step, our oxygen on the carbonyl group grabbed a proton from hydronium cation, and you get this compound. So why is this a better electrophile than this guy over here? The reason why is because we've created a positive charge now. So if I do resonance and push up this pi bond, then you're going to get that same positive charge on the carbon. And now we have to decide, does the positive charge want to be on the carbon or the oxygen? Well, we know negative charges like to be on electronegative atoms, so by that logic, your positive charge wants to be on an electropositive atom. We know our carbon is more on the left on the periodic table, so it's more electropositive, so it would rather spend more time on this carbon. And because of that, the positive charge spends more time on the carbon, making it more electrophilic and more reactive. So that's the purpose of protonating your carbonyl. The positive charge will stay on that carbon longer, making it a better electrophile. So now we have our protonated carbonyl we just formed. And what's going to happen is now it's easier to abstract this alpha proton. So our weak base, water, is able to come in and just grab this proton. And remember, we can't use a strong base like NaOH because we're in acidic conditions now. So it's going to abstract this proton. This bond's going to kick off and form a carbon-carbon double bond. And this pi bond is going to go onto the oxygen, forming an alcohol. So this group we've seen before, this is called an enol, because there's an alkene and there's an alcohol. So that's where the name comes from. Now this enol we just formed is going to attack another one of these protonated carbonyls we just formed. So the enol plus the protonated carbonyl. And remember, this protonated carbonyl is a good electrophile, so it's easy to attack it now with this enol we just formed. So here we create the product of this attack, and it's almost close to being that beta hydroxy carbonyl group that we're looking for, but this carbonyl is still protonated, so we need to grab that proton off. So some water is going to come by and it's going to grab that proton, and this bond is going to fall back onto the oxygen. So here we created that beta hydroxyaldehyde that is the product of our aldol formation step. Well, now remember, for step 1, we can create our aldol, but in step 2, if we add heat, we can also do condensation, remove that water, and form a double bond in its place. So let's see how the acid catalyzed mechanism does that. Now, just a warning, this was the mechanism I learned when I took organic chemistry, but there are some disputing mechanisms for this part of the acid catalyzed mech. So if your professor shows it to you one way, just use that. But this was what I saw. So what's going to happen here is that your carbonyl now, instead of your OH, which is a bit weird, it's going to grab this proton, and it's going to get protonated, becoming a better electrophile. And because of this, it's easier to now to abstract this alpha proton that's sitting here. So your water is going to come in, grab that proton, and then again, it's going to form an enol group. This enol is now good because we are going to use it in our fourth step of our reaction. And remember, the whole point of this is we want to get rid of this OH group and this hydrogen sticking off here. Well, we just got rid of the hydrogen in this step because we attacked it with a base. Now we somehow have to get rid of the OH. Well, we're in acidic conditions, so we can make this a good leaving group by protonating it, forming an oxonium cation. And that's what we did. So now we have the enol on the right we just created from our first two steps, and we have this protonated oxonium we just created in the third step. So now they're going to perform a concerted mechanism where the lone pairs from this oxygen are going to come down, push off this double bond over here, and then kick off the oxonium. And what you're going to be left with is this product. And then in the last step, you're going to get rid of this proton because you don't need this here. So you form your Aldol Condensation product using acid catalysis. So this is what your final product should look like. Again, some textbooks, sometimes they show it just with protonating this OH and then kicking it off. This was the one I was shown, so just take it with a grain of salt. So let's look at some practice questions now. So here, if we start off with two aldehydes, we can do an aldol condensation if we add a strong base. So here we're using potassium hydroxide. So what your potassium hydroxide is going to do is it's going to abstract a alpha proton from here, and you're going to be left with this. I'm not going to draw on the H for simplicity. So now you have a lone pair on this alpha carbon. This is a good nucleophile, and lo and behold, we have our electrophile. So we can attack it and kick up this pi bond. Let's use purple to show the bond we just formed. And remember, there's still a hydrogen here, and that's why there's 3 bonds in the hydrogen in the back that I'm not drawing in, but I just excluded it for clarity. And then we have this blue enolate we just used to attack. So this carbon right here is this carbon. So now it has 2 things, a methyl group and this. So let's draw the methyl pointing down because that's not as important, and let's keep the aldehyde up. So it looks more similar to what we've been working with. A lot of people get this part confused because this methyl is pointing up and then this methyl points down, and you really don't have these colors to help you understand it on exams. So just understand that this bond can rotate and push this methyl down. Alright, great. So we have this, and we know we're going to protonate it. So let's just get rid of this negative charge and add in a hydrogen to get your beta hydroxyaldehyde. And now remember, in heat, we can get rid of this hydroxide and this hydrogen over here, and we can replace it with a double bond. So that's what we're going to do now. So here we created our double bond and got rid of these 2 groups. Now let's think about stereochemistry here. There's a reason why I made it like this and didn't put the red one up. If I look between our CH3 group and our aldehyde, it looks like our aldehyde's a bit bigger. The reason being it has a carbon just like the other one, but then it has an additional oxygen on top of it. So it's just a little bigger. And we know we want to place our biggest groups as far apart as possible. So we want this molecule to be trans. So the big group on the left side and the big group on the right side are on opposite sides, which is good. If I had the cis, then it would be more steric hindrance. So just pay attention to the stereochemistry of the double bond you form. So let's do this example now. We have these two acetone molecules, and we know that our base is going to form an enolate on one of them. So I'm just going to draw on the enolate now. On this alpha carbon, it's going to take off that proton, and then it's going to attack here and push up this pi bond. So let's draw what we're left with. So this oxygen should have a minus charge. And now remember there's a methyl, but the methyl is going to get in the way of the bond we're forming. So let's just put the methyl down for right now because it's just getting in the way. Let's use purple to denote the bond we just formed, which is from this arrow right here. And then blue to finish off what we started, so it goes like this. And now we're going to protonate this oxygen because it's going to grab a proton from solution. And we formed our beta hydroxyketone. So that's from our aldol formation step. Now we also need to do an aldol condensation step. So in heat, we know our OH and our hydrogen are going to fall off and be replaced with a double bond. So let's draw in what that looks like. That looks bad. So this is the product of the aldol condensation. So one quick thing I want to point out to you guys is look at the equilibrium arrows I have between the two aldehydes versus the two ketones. Here the equilibrium greatly favors the aldol, but here it greatly favors the ketones. And the reason why this reaction doesn't go forward as well is because there's a lot of steric hindrance here. We want our enolate to be able to come in and attack this electrophile, but these two methyl groups sticking out make it a bit harder. Whereas here we have a hydrogen sticking out here, and that's barely anything, so we have sort of a point of entry. So it's easier to attack, which is why the equilibrium is shifted right. So now I showed you examples of two aldehydes reacting and then two ketones reacting, but sometimes we can have a mix. But when we have a mix of things, it gets a bit tricky because there's a lot of places where we can enolize. So to make this more high-yield reaction, we have to do one of two things. We can either make something non-enolizable. So if we look at this compound on the right, we have benzaldehyde. If we look on the left, there's no alpha proton because this is a benzene group. And if we look on the right, there's no alpha proton because this is just a hydrogen. So this entire group is non-enolizable. So if I add base, it's not going to form an enolate, which is good because then we won't get any minor products. The other thing we could do is we can find a symmetrical group. Here we have cyclopentanone. Cyclopentanone has a axis of symmetry right down the center. So if I form an enolate on the right side versus the left, it doesn't matter because this compound is meso. So because of that, there's only one product you can form. But if I added like a methyl group here or something, then you're going to get a lot of products and it just gets messy. So let's draw in what happens again. So we know the one on the right is non-enolizable. So let's start off with what's on the left. So we're going to abstract an alpha proton, and it's going to come in. Oh man, that was messy. And it's going to come in and grab this it's going to attack and push up this pi bond. So you should be left with this. And I'll use purple to denote the bond we just formed. And we know we're going to form a beta hydroxy ketone or aldehyde, whatever it is. So let's already just draw in the OH and then figure out where we are. So we know that the OH is connected to a carbon, which is connected to a benzene. So the OH is connected to a carbon, which is connected to a benzene. Sometimes it'll help you to just word it out like that so you don't forget where you are and don't like miscount a carbon. So this is the product you should get. And then if you end up adding heat to it, you can form your condensation product. and you'll end up losing water. It's honestly, when you do these condensation, it's easy to just think of the base catalyzed mech, which is basically a base comes in, grabs this proton, and then you do E1CB and kick off this OH. So that's a good way of thinking through it on exams, because the acid catalyzed mech is too long. So you should be left with this. And this pH is just for phenol. I don't want to draw it in again. But yeah, so these are just a few examples of aldol condensations. So now let's look at the more interesting examples, the stuff inside of us, the biochemistry behind this. So this is just a light overview of what cell respiration is. We know when we start off with sugars that we eat, like from candy, they come into our body's glucose, and through glycolysis, they're metabolized to a 3-carbon compound called pyruvate. Then pyruvate can enter the mitochondria as a 2-carbon compound called acetyl-CoA, where it can participate in the citric acid cycle. Here, it combines with a 4-carbon oxaloacetate to yield citrate, which then carries the cycle through. In your cycle, you form these high-energy electrons that can be used by the electron transport chain. So the reason why I'm just showing you this overview is because I want to focus on 2 reactions from this entire pathway. The first step will be the reaction of acetyl-CoA, which is a 2-carbon compound. You can think of acetyl group looking like this. It's a carbonyl with a methyl, and then you're going to have just CoA on the side. So the CoA is not part of this, so just think about 1 carbon, 2 carbon. And then you have oxaloacetate. And these 2 and 4 carbon compounds combine to form a 6-carbon citrate. And citrate's actually pretty interesting. It's what this entire cycle is named after, so it's a pretty important reaction, as it's the first step of the citric acid cycle. So let's see how it relates to the aldol stuff you guys have learned today. So as I said before, here we have our 4-carbon oxaloacetate and our 2-carbon acetyl-CoA. So what's going to happen is they have to somehow combine to form a 6-carbon compound. So in base, we're going to abstract a proton from this alpha carbon of the acetyl-CoA. So your acetyl-CoA will be acting as your nucleophile, and it will attack this carbonyl group. So these 2 red carbons I drew in are going to be these 2 carbons on the side. And let's draw in where everything is here. So we're going to attack this carbonyl and push up this oxygen. So we should be getting an OH. So that's going to be this OH over here on the middle. And then these 4 carbons are these guys right here. So this one, this one, this one, and this one. So hopefully the colors help you orient yourself, because it's a bit tricky. But we know that if we form our nucleophile here, it's basically going to attack here. So this is the bond we're forming. And that bond that we formed is this bond right here in purple. So hopefully that gives you guys some orientation. Let's draw out a sample mechanism of what happens here. So let's say I do form this enolate, and then I attack this carbonyl group. So let's see what I end up getting from that. So we know that when this nucleophile attacks this electrophile, we're going to form an OH here. So let's draw that in. And let's attach our 2 red carbons to where we just attacked. I'm going to draw purple to just show the bond we just formed. And then carbon 1, and then carbon 2. And we have our CoA group is still attached to it. So this is our CoA, but in our final product, our CoA is gone. because it's gone here. So how we get rid of it is we still have water. So water is going to come in, and it's going to act as a nucleophile, and it's going to kick off this CoA. The reason why we can kick off this CoA is what it looks like if I sort of take this and magnify it is CoA is actually a thioester bond. It has a sulfur group and then the rest of the big functional group. Thioesters are actually very high in energy, and the reason why is because there's a very large positive charge on this carbon now. The reason why is because you might think, okay, sulfur can participate in resonance and donate electron density, therefore there shouldn't be a positive charge. But resonance, as it's defined in every textbook, is the overlap of p orbitals. So there needs to be good overlap in order for resonance to occur. Your carbon is in period 2, while your sulfur is in period 3. This p orbital in your sulfur is much larger, so this overlap is pretty bad. And because of that, your sulfur can't donate electron density. Therefore, there's going to be a much larger positive charge on this electrophilic carbon. Because of that, this entire moiety over here is very reactive. So your water can come in, and it'll just attack and then kick off this CoA, and you should be left with this citrate. So this is the organic chemistry mechanism behind it, but it doesn't happen like this in our body, of course. So let's see what the enzyme does. And the enzyme that catalyzes this is, I believe, citrate synthase. Yeah, citrate synthase. So there's 4 steps. Let's go through what happens one by one. So let's just orient ourselves. Here we have our acetyl-CoA. So I think I drew it in red last time, so let's draw it again in red again. So we have our 2 carbons. And I showed you our CoA actually has a sulfur group, which just makes this a high-energy thioester bond. And this is important for removing this CoA later on. And we know our CoA is going to act as our nucleophile, so the first step should be its deprotonation. And in order for it to be deprotonated, we need a good base. And if you guys remember from your amino acid unit, there's 3 basic amino acids. There's histidine, lysine, and arginine. So in this case, we use one of those. We use histidine because histidine is pretty basic at a physiological pH. And it's going to use one of the nitrogens on its imidazole side chain, and it's going to grab this alpha proton and form an enolate. So here we formed an enolate of our acetyl-CoA. So we create this enolate. And over here we just still have our oxaloacetate, OAA, just sitting over here waiting to be attacked. So in our second step, our enolate is going to come in and it's going to attack our oxaloacetate at this carbon. So let's draw what we get. So remember the acetyl-CoAs, the 2 carbons were red, and then I believe I made the other ones blue. And this oxygen that gets pushed up forms a hydroxyl group. So this oxygen is a different color. So what we should get in this molecule is this oxygen over here is still green. And then let's see what else we got. So these 2 carbons are red because they came from the acetyl-CoA. I'll draw a purple bond to indicate that this is the bond we just formed. And we have the 4 carbons from our oxaloacetate. And then this isn't the finished product yet because we know our citrate doesn't have this CoA, so water is going to come in and do addition elimination and kick off this CoA group, and you'll be left with citrate. And the funny thing is, this citrate is named after, this Krebs cycle is named after citrate for 2 reasons. One, it's called the citric acid cycle, so that's how I get the name. The other one, this group has 3 carboxylic acids, one here, and one here. So that's why the Krebs cycle is also known as the TCA cycle, the tricarboxylic acid cycle. So it's a pretty important reaction, so I would keep that in mind. It'll help you guys for biochemistry. So now we've looked at aldol reactions in the forward direction, both in organic chemistry and in biochem. Now let's look at the backwards reaction. So here I have that beta hydroxy ketone we've been dealing with so much. So now if I add acid or base again, I can shift the equilibrium the other way, and we can get our original starting compounds. It may seem a bit daunting to figure out, okay, how did I start off? I'm going to miss a carbon. So I'll show you a trick for how to get through this. So you start off and you identify, okay, this is the carbonyl and this is the OH. They're both beta to each other, so this is the main part of the reaction. The rest of this is just irrelevant. So you find your OH, and then you take a lone pair on your OH, kick it down, break this bond that we had formed, and then push up this O-. So a set of 3 reactions, and then see what comes out of here. So on the left, we should be getting this cyclohexanone. So now this becomes an O-. And here this bond breaks, so you should get a double bond here. Okay, cool. Now let's figure out what's going on over here. Well, I just drew this chair to mess with you guys, but this chair is also a cyclohexane, you guys know that. So again, let's draw it as a cyclohexane to make it easier on the eyes a bit. And we know that this O is going to come down to form a carbonyl group, and it's still going to be protonated, but we can take off that proton. So this guy can just take off that proton, so this guy gains 1, this guy loses 1, and you should just be left with 2 cyclohexanones. So it can work in the opposite way too. This is called the Retroaldol reaction, and used to form 2 carbonyl groups. Just remember the trick I showed you. Start with your hydroxyl, use its lone pairs to push down, break the bond we formed, and push up the carbonyl. We're going to use this now in a biochemistry application. So here, this is glycolysis. This is the 10-step reaction to form 2 3-carbon pyruvates from a 6-carbon glucose. And it produces 2 ATP and 2 NADH also. So there's a very interesting step here. We go from 6 carbons to 2 3-carbons, so there's somehow a breakage happening. And this breakage happens in this step where there's a bifurcation in the reaction. So our fructose 1,6-bisphosphate turns into dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. And this mechanism is catalyzed by an enzyme called Aldolase. And I hope that sounds familiar from what we've been doing. So it happens through a Retroaldol reaction mechanism. So let's see how this works. So we have fructose 1,6-bisphosphate, and let's see what's going on. So 1,6-bisphosphate. So on the 1 carbon we have a phosphate group, and on the 6 carbon we have a phosphate. So instead of saying di in biochemistry, you guys say bis. So that's just a new nomenclature. And we know it's a D sugar because this penultimate carbon has a R stereochemistry. So that's why it's D-fructose and not L-fructose. And yeah, so this is the sugar we start off with. It has 6 carbons. So we know we have to break it up into 2 3-carbon products. So essentially, we're going to be breaking this bond over here. And if we look at it, well, we have a carbonyl over here, and we have a hydroxyl. And are they beta to each other? Yes, because there's a carbon in between. So this is a beta hydroxy ketone. And that sounds familiar from all these aldol stuff we've been doing. So this is actually the aldol product. But we can shift it the other way using the aldolase enzyme and get our carbonyl starting products. And that's what we do here. So what's that trick I showed you guys from up here? You take your lone pairs on the OH, push them down, break the bond we formed, and push up the carbonyl electrons. We do the exact same thing. Let's see how it works. So you take your lone pairs on the oxygen, push them down, break this bond we just formed, and then push up the carbonyl oxygen. And you should end up getting this glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. So this comes from the top, and this comes from the bottom 3 carbons. So this is just the mechanism to show you guys what happened here. So when we do this, your aldehyde forms fine, your glyceraldehyde 3-phosphate from the bottom. But the problem is for your top 3 carbons, you actually form an enolate. So the way you can just fix that is just you add a acid, and then you should be able to get your dihydroxyacetone phosphate product. So let's see how an enzyme actually catalyzes such a complex reaction. And there's a lot of steps, so I hope you guys are prepared. And remember, the enzyme is aldolase. So let's see what happens. So before we start anything, remember, all reactions occur in the active site of an enzyme. So in this white active site we have 3 important side chains that are projecting inwards. At the top we have a lysine, and if you remember, a lysine is a basic amino acid, and it has an amine functional group at the end. The middle one we have is a thiolate. This is a cysteine, but it's just deprotonated, and it looks like it could be a good base, so let's just keep that in mind in the future. And here we have histidine, and histidine also is a basic amino acid. So it seems like we have 3 very basic things going on, and that seems to make sense considering that this reaction occurs in base, right? So let's see what goes on. So our fructose 1,6-bisphosphate somehow has to get attached to this active site. And one way we can tether it in there is by reacting this carbonyl with this nitrogen. And if you guys remember from our carbonyl unit, this is how you form an imine Schiff base. This is a very important first step, so I hope you guys take note of that. Your aldolase sort of binds to this substrate by forming an imine shift base. So this nitrogen from this lysine attaches to this oxygen, and this is what you get. So this is just like a tethering mechanism, so it doesn't float away. And now this fructose 1,6-bisphosphate is here to stay until it finishes reacting. So now let's proceed with the reaction. So the first thing we do is we form an imine here, I-M-I-N-E, an imine, and let's form a good leaving group out of it. So in order to form a good leaving group, we know we have to protonate it. So let's grab a proton from solution, and let's form this hydrogen here. So here we formed an iminium ion from the imine, and we created a good leaving group. So let's see, what's the purpose of this good leaving group? Well, we'll take advantage of it in the next step. What's going to happen is your thiolate from your cysteine is going to act as a strong base because it has this negative charge. And what it's going to do is it's going to come in here, grab this proton, push off this bond to form a carbonyl, and then it's going to break this bond we had formed, and we're going to push this up. So this is taking advantage of that good leaving group we formed because we're pushing up this pi bond. Although we're not kicking this entire group off, we're still causing it to quote-unquote leave because this pi bond is being kicked off. So the point of forming this this iminium cation was that so we can do an elimination reaction. So let's see what the product of this elimination gives. We should end up with 2 3-carbon products. So on the bottom, this is your aldehyde, your glyceraldehyde 3-phosphate. So that's cool. We formed our aldehyde, but our ketone still looks pretty messed up. So we still have more stuff to do. So our G3P is just going to leave, and let's focus on what's going on with our DHAP. So somehow we have to convert this back to its ketone form. And we know we can't really hydrolyze an imine, but we can hydrolyze an iminium cation. So first, let's form our cation, and that's what we do. And then if you add acid, it'll hydrolyze this iminium cation to give you the ketone group. So this is your dihydroxyacetone phosphate, because there's 2 OHs, and one of them contains a phosphate group. So this is sort of the mechanism behind a retroaldol synthesis in your body. So it's pretty cool. It's a very important step in glycolysis. So I would commit these 2 biochemistry mechanisms to memory. And let's look at one last concept. This one is not too bad because we've seen this before. It's similar to aldehydes and ketones, but instead of using those 2 groups, we're using esters. So now this isn't called an Aldol condensation anymore. It's called a Claisen condensation. So let's see what happens here. Well, we're going to use base to create an enolate. So if I look here, can I create an enolate on the left? No, because there's no carbon. There's no alpha carbon. If I look on the right, there's an oxygen because it's an ester. So I can't abstract a proton from an oxygen. There's nothing there. So this, what you would say, is non-enolizable. Now let's look at this red one over here. If I look to the left, oh, well, there is a proton sticking off here. So I can enolize that. So let's keep that in mind. And to the right, we have our methoxy group because this is an ester. So I can't abstract a proton on the right. So there's really only one proton you can take, which makes this a very specific reaction, which is good. So what you're going to do is you're going to form an enolate anion, and it's going to come in here, and it's going to attack this ester group. So let's see what happens now. So our carbonyl is pushed up to form an O-, and for the sake of everything, let's just push this group downwards because it's just it's very big and annoying to work with. So that's the one thing I want you guys to be able to take away from this is that be able to like rotate around these bonds and push this like useless crap out of the way because it's not going to be helpful and it's going to just sort of misguide you on this reaction. So now let's use purple to denote this bond we just formed. So it should be like that. And now let's add in this red enolate we just used. So once again, let's push this methyl group down because it's just annoying to work with. So these 2 methyl groups are down, and now we have this up, and our methyl ester is formed. So this is what we should get, somewhat. But remember, this O- has to be gotten rid of. So how do we get rid of it? Well, there's 2 ways. Either we protonate it, or we can do addition elimination. And remember, esters can undergo addition elimination because when this leaves, it would form a weak base, which is good. So this O- is going to come down and kick off this group over here. It's isopropanol. And we should be left with this product. So this is what you should be left with. And this isn't the beta hydroxy ketone you guys are used to seeing. Instead, you get a beta keto ester. The reason why is because you have a ketone on the left and it's beta to this ester. So that's the important distinction you guys have now. With an aldol condensation, you form a beta hydroxycarbonyl. With a Claisen condensation, you form a beta keto ester. And the reason why there's this distinction is because this ester can do addition elimination, and it'll come back down to form a carbonyl group instead of staying as a hydroxyl. So just keep that in mind. But if you guys understand the principles, this reaction shouldn't be too bad. So now I'm just going to give you guys some homework questions if you're in my class. There's 4, but they're pretty short, nothing too crazy. If you can just send in a picture to me by the end of the week, that'd be good. So here, think intermolecular, because there's 2 carbonyl groups. So let's see what happens over there. And remember, there's heat. So remember what heat does in an aldol reaction. That's the only hint I'm going to give you. Here, this is an example of a Claisen condensation. And these 2 are just sort of conceptual questions about the biochemistry we did today. So I hope this was helpful. If you guys have any questions, feel free to leave a comment or message me, and I'll try and get back to you guys. Stay safe.